Okay, so let's take a look at Jupyter notebooks from this lecture, overview of mathematics. So there are five notebooks posted for that lecture. So we'll just briefly overview those. So Python NumPy arrays. So in Python, when we do the computations, we rely on the NumPy functionality. NumPy is the primary library for numerical computations. Basically, in Python, we can do this high efficiency mathematical computation. Це обов'язково частина.
Новорічний настрій, а як без цього?
У нас приходиться.
Да, сердцевед такая, да?
Пакетик.
Самый любимый.
Що робити з пакетиком?
Нічого, дивитися.
Это только тебе, нам по сиропу.
Может, пакетик дивитися.
Дякую. Красавці.
So NumPy is the primary library for numerical computations in Python, where we can define different types of data structures, mostly arrays, vectors, matrices, to do vector and matrix computation. So what we can do, we can define just a list in Python and after convert it into the NumPy array. And of course, NumPy arrays are much more efficient for computations than Python lists or tuples or any other native data structures. So we can also define two-dimensional arrays in Python, can be three-dimensional, and so on and so forth. So that's the definition of the two-dimensional array, which has 2 rows and 5 columns. Pretty much the rest of the notebook is how we can work with those arrays, how we can define, reshape those, so we can define the identity array. So that's our equivalent of identity matrix, which has, in this case, 3 by 3 dimensionality with 1s on the main diagonal and 0s everywhere else. We can also define identity matrices which are not square matrices. So in this case, 3 rows, 5 columns, and their diagonal is shifted 1 index to the right. So their ones are not starting from here, but starting from here. So we can define the matrices, the arrays of all ones, the arrays of all. So the array of all zeros. With NP0s, we define the arrays of all zeros. In this case, the dimensionality 3 by 4, or Christmas t-shirt. So we can also index these elements of the arrays by an index. In this case, we are getting the third element of an array, because in Python indexing starts from 0, so this is 0, 1, and 2, so it returns 3 for the second index. We can also do slices of the arrays. So in this case, it returns the elements starting from 4 till the end of the array, which are the 2 last elements of the array. In this case, this is a shortcut to reverse the array to print it in the opposite direction. We can also stack the arrays together, so we take our array and after that add the second row with 10s added to every element, after that the third row with 100 added to all the elements. In that case, then we have a 2-dimensional array, so we can specify the 2 coordinates, second row, third column, and in our case, the second row, because indexing starts from 0, 0, 1, 2, and the third column is 0, 1, 2, 3. It's another slicing and dicing of the arrays, it's another slicing and dicing of the NumPy arrays. So there are a number of commands to reshape the arrays. I will probably not go through all of those. So we can use the reshape to reshape the dimensionality of the array. We can unravel the array from multi-dimensional to one-dimensional, in this case by rows. or in the opposite case by columns. And we can flatten the array, we can transpose the array with dot T notation. The dot T notation, and so in this case as a standard transpose. So we can flip the array vertically, flip the array horizontally, we can rotate it 90 degrees, we can shift elements along a given dimension, and so on. Just looks quite a number of different operations, and of course we can do mathematical operations on the arrays. One thing to remember that arrays are not really matrices. So that's why all operations on the NumPy arrays are pretty much element-wise. So in this case, yeah, when we add 10 to the array, 10 is added to every element. Now for matrices, it's the same in this case, so addition is element-wise for matrices. But when we multiply the array, it's not, it's also element-wise operation. When we square every element of the array, element-wise operation. And yeah, adding two arrays of the same dimensionality, element-wise operation. But when we multiply two arrays, it's not matrix to matrix multiplication, it's also element-wise multiplication for the NumPy arrays. Something to remember, so for NumPy arrays, the operations are element-wise. Even if you multiply one array by another, in this case, it's not a matrix by matrix multiplication, it's element-wise multiplication.
NumPy arrays, NumPy.
No, NumPy is a library in Python for numerical computation. So it's one essentially mathematical library to deal with matrices, vectors, arrays, and multidimensional objects. So it supports standard operations, summation, taking the square root of every element of the array, computing the mean, and so on. Now, if you want to really do the matrix by matrix multiplication, so we should use the dot operation. In this case, is np dot. These two arrays are going to be multiplied as matrices or vectors. If those are vectors. So that's that part about the arrays in NumPy. We can also do matrix computations with NumPy. So as I said, by default, the operations on arrays in NumPy are element-wise, so summation, multiplication, subtraction, and so on. Division is element-wise, the remainder is element-wise. So if you want to do matrix operations, we have two choices. Either use the dot product, np dot. In this case, x and y are multiplied as vectors, or as matrices in general, or we can convert NumPy arrays to matrices. So we define the two NumPy arrays. And here, when we multiply those are element-wise multiplication. So in this case, 2 is multiplied by 1, 3 is multiplied by 2, so we get 6, and so on. If you want to do the matrix multiplication, we first convert those NumPy arrays to matrices, is an p.matrix. And after that, when we do x multiplied by y, this is matrix by matrix multiplication. This is all the matrix rules for multiplying one matrix by the other. And of course, we get different results as compared to the element-wise multiplication. So this element-wise multiplication, this is the matrix by matrix multiplication. We can do this same with np dot, so without converting NumPy arrays into matrices. So we can do this matrix to matrix multiplication. Or we can also do it this way. Convert to matrix the array x, convert to matrix array y, and do the multiplication. And here are some examples how to do it. So some of the computations we have done yesterday, so we can define this 3 by 3 matrix that we used yesterday in one of the examples, and we can compute eigenvalues and eigenvectors. So those are the eigenvalues that we computed yesterday, 4 to 5. We can compute determinants. The determinant of function in NumPy, and so on. Okay, so there were also examples for solving systems of linear equations. For solving systems of linear equations in Python, we use SciPy library. So this is a library for scientific computations in Python. That's why it's called SciPy, scientific computations in Python. And that's typically on the top of on the NumPy library itself. So if you want to really check what this operation is doing, we can use, let's just run it. So what we can use, so if I want to know what this LA linear algebra command is doing in this, I can put the question mark at the end, run this cell, and it shows me the help. So this shows the help in Python with all the, so this LA defines linear algebra functions, and you can read all the help, all the operations for the linear algebra functions. We will look at some of those. So and the same here, if I want to figure out what LA.solve is doing, run this and it shows, okay, so this is going to solve a system of linear equations, A multiplied by x equal to b for the unknown x. So LA solve is solving a system of linear equations. LU factor do the LU factorization. Now we'll get to that. So when we have this system of linear equations, these three equations are unknown, we write it down in our traditional vector and matrix form, with matrix A being this, with vector B being that. After we define A as a NumPy array and B as a NumPy array, and when we give A and B to the LA solve, it returns as a solution to the system of linear equations, which is 0 minus 1 minus 1, or 0 minus 1 plus 1.
LA solve.
Yeah, LA solve.
Can you please explain what does dots means?
Sure, okay, so dot means what we did when we imported this library, so the SciPy.
Not the dot.
The dot
Return to
between.
matrix, please.
Метод просто.
Not matrix. But when we have in array 8 dot, comma, 4, comma, 6, comma,
Well,
what
it's-
does that mean?
Again, in this case it's not really necessary, it shows you that this is a floating point number instead of integer number. So in the previous version of Python, Python 2, if you do not put the dot, it treats it as integer and applies the operations to integer numbers. In Python 3 it doesn't really matter, you can remove the dot, but otherwise it means 8.0. It's a decimal dot. Same there. Again, this is typical legacy from previous version of Python, so you should define at least one element as float, so that it treats all elements in the arrays as float in point numbers instead of integer numbers. Again, legacy stuff, we don't need it anymore. And again, yeah, in English we use decimal point instead of decimal comma. As always. And after that, we can check if the solution holds of this. So we have our array A, our array X, and of course when we do A multiplied by X, because it's an element-wise multiplication in NumPy, so we're not really getting the vector B as expected, so instead of doing this, we should use the dot product, and in that case, to verify the solution, so we should get the dot product, A multiplied by X. In that case, matrix multiplication is applied, and we get the right inside vector B, which was 8, 4, and 6. So we verify that the solution is correct. Yeah, we can compare basically if we should get zeros as expected by subtracting the right hand side computed from the right hand side that we have. Okay, so another way to do it, so if you need to solve a number of linear equation systems with just different right-hand side, with different right-hand side vector B, what we can do first the LU factorization. So this is essentially the factorization that we have done yesterday. That's Gaussian elimination, where you, from your matrix A, you factorize it into the lower triangular and upper triangular matrices L and U. And after that, you can substitute different right-hand side vectors B, and you don't need to resolve, because you have done your factorization. All what you have to do, you have to basically minimize the number of operations that you need to do, and matrix P is the permutation matrix. We may permute rows and columns of our linear system to speed up the solution. So the permutation matrix is looks like this. What it means is in this case, the row 2 and the row 3 are getting permuted, and that really helps to speed up the solution. After that, we get the lower triangular matrix, we get the upper triangular matrix from our factorization, and now we can use it in our computations. So if we, how it's done, so because we factor A into L and U, so what we can write it down, L multiplied by U multiplied by X equal to B. After that, we solve L multiplied by Y is equal to B, and after that, we solve U multiplied by X is equal to Y. Essentially, in this case, because we already have our factors, we can solve the system of linear equations for different values of D. And that's doing the next example. So we have our matrix A and we have two right-hand side vectors B. So what we do first, we do the LU factorization. And after that, well, we can solve directly, but in that case, you need to solve two systems of equations for right-hand side B1 vector and right-hand side B2 vector, which is inefficient numerically. But if we do the U factorization only once, and after all you need to do the back substitution 2 times to resolve for B1 and B2, so you are saving a lot on the computational efficiency. So that's pretty much it. So solving system of linear equations. And we also discussed yesterday solving nonlinear equations and systems of nonlinear equations. So here we can visualize this system of two nonlinear equations, these two unknowns. So what we do first, we plot these two functions, and after that we want to find the solution, which is here. As you see, the solution is 1, 0. And after that, what we can do, we can apply our Newton algorithm, which is implemented as fsolve function in the SciPy optimized package, and it's going to solve this systems of two linear equations. So the first linear equation is x1 cubed plus x2 minus 1 equal to 0, and the second nonlinear equation is x2 cubed minus x1 plus 1 is equal to 0. So we basically implement our function that computes those equations, and after that we apply the function fsolve, which is the Newton algorithm we discussed yesterday, to solve this system of nonlinear equations starting from the point x0 equal to 0.5, 0.5. Again, all what we have done yesterday, and we get the solution 1, 0, and we can verify that, substituting this solution into equations, we should get 0, 0. Yeah, we get small numbers, 10 to the power minus 10, which is essentially 0. So that's application of the Newton algorithm to solve the system of nonlinear equations, and as we remember from yesterday, we can apply Newton algorithm to minimize function as well.
0.
I think this equation y0505, this is just a random starting point.
Yeah, it's a starting point. If you don't have any other idea, we start from a random point. If you have a good idea from which point to start, which happens sometimes but not too often, in that case we supply that starting point that hopefully speed up the solution.
Where is converge interval? There is some default here?
Yeah, there is some default. So as you see, it's not exactly 0, it's 10 to the power minus 11, which is a small number, so I think it's the precision is around 10 to the power minus 10 or something like that by default. Yeah, but you can change it if you want. So just reading the documentation about the fsolve and pretty much figuring out how to change the precision. So I'm sure that there are some parameters here where you can go and change the precision of the solution. Another Jupyter notebook, that's the last one, shows how to do two algorithms for solving system of linear equations, bisection method that we didn't discuss too much, and the Newton method that we discussed yesterday. So for the Newton methods, so here is the basically the same formulas that we derived yesterday, and as remember, that's what it's doing. That every iteration is building the line which is tangential to the current function until we converge to this to the solution. So in each iteration we solve a linear equation or a system of linear equations. And here we have the implementation by hand. It's pretty much very simple. So what we are doing at every iteration, to compute the next point, we take the previous point minus the function value divided by the function first derivative, and that's all what we do in the Newton algorithm. Of course, we should be able to supply the derivative, so how the derivative is computed. So we need to define two functions, the function f itself and the derivative function that computes the derivative of our function f. And after that, we substitute these two functions, our function and derivative function, into the Newton method implementation with tolerances, maximum number of iterations, and so on. And all what we do, we iterate from one iteration to another, moving from initial point, which is access, to the next point in the loop until either the maximum number of iterations is exceeded or until we reach the precision tolerance. So one or the other. And when we reach the precision tolerance, we stop, or if the maximum iteration is exceeded, we stop as well.
But I guess there should be some library which provides some method already.
It's all in SciPy. This just manual implementation to understand.
Yes.
Basically, in many cases it's useful to look. So we derived the formulas yesterday. So this function is essentially implemented in the same formula that we derived yesterday for the Newton method, but with some computer science things such as you define the tolerance, the stopping criteria, when should you stop, which we didn't really do when we derive it mathematically. It defines the maximum number of iterations, so you don't go forever, and so on. So it even tells you whether you should print those iterations or be silent, and so on.
So yes, it was modification, but if you already understand, then you can...
Of course, if you already understand, you use the built-in Python libraries such as SciPy in this case. But here, essentially, what we do, we give the two functions to this procedure, and we basically run Newton method for one function, it converges, we run it for another function, it doesn't converge after 10 iterations. So there are some cases, there are some functions for which it does not converge. That's something else to take into account. So that's another example for another two functions. And after that, you can use just SciPy optimize, which has a native implementation of the Newton's algorithm. And you can use, as you said, those built-in functions. So either have solve, which is a standard implementation of the Newton method. And after, you can also plot the results when you find the root, when your function is equal to 0, nonlinear function, or you can also apply to minimization. So as you know, Newton method can be applied both for solving systems of nonlinear equations and for minimizing a function. Okay, all Jupyter notebooks are there, so we have around from 2 to 5 of those for every lecture. So again, feel free to reuse those in the projects that you do in the other courses, and that's a goal. So for you to be able to reuse those Jupyter notebooks in your future studies. So that's why those are here, and you have some point to start when you have a project from one of those notebooks. So there is a good chance that there is something similar in the examples for your project. And we'll discuss the course project as well today. Okay. Any questions? Now we come to modeling. So, and this lecture we will talk about the regressions, linear logistic regressions, which are essentially one of the three main algorithms of data science or machine learning, whatever you prefer to call those. So regressions are still heavily used, both linear regression and logistic regression, and as long as we can understand how the regression algorithms work, we can pretty much understand any other machine learning algorithm, because the principles are the same. As we slightly touched base yesterday, in supervised machine learning, our goal is to, let's write it this way. So essentially, our goal is we have a target variable, which can be either quantitative numerical in other terms, or can be discrete. Typically, discrete binary can be 0, 1. So it's either continuous or discrete, the target variable. If it's discrete, typically it takes value 0, 1, or can be 0, 1, 2, 3, 4, 5, so on. So this is, in machine learning, our vector of inputs into our machine learning algorithm, and those are typically called features that are telling us something about the problem that we are trying to solve. And let's actually look at one of the examples what that means.
It's always continuous, yeah? This feature.
X, no, it can also be discrete, 0, 1.
Is this dummy features?
Yeah, if it's dummy variable, it's 0, 1. So in that case, that's what we have. Let me actually show you an example of that was in lecture 2, just we didn't get to it because we're going to see it later in any case. But let's do an example of a data of a natural language processing problem that we can solve with this type. So yesterday we touched base slightly about sentiment analysis. So in sentiment analysis we have a piece of text and we would like to model whether it has a positive sentiment, neutral sentiment, or negative, or in the simplest case, just either positive or negative. Typically applied to tweets, Facebook posts, and so on. And this is one of the algorithms of text analytics, natural language processing, called sentiment analysis. We would like to figure out what is the sentiment of a piece of text, like a tweet, Facebook post, news article, and so on. And if we are talking about just positive or negative sentiment, yeah, our target variable is discrete, either 0 or 1. So, positive or negative sentiment. So, we can take two values. Now we need to figure out what are our features in this case. So, let's say that we have 5 tweets. So, those are called examples in machine learning. Can be news articles, can be tweets, can be Facebook posts. So the first tweet, all bears are lovely. Second tweet, our key was bad. Third tweet, that bear drinks is there. Fourth tweet, the bear drinks tea, and we love bears. So now, first, what you do in machine learning, you ask somebody to label the sentiment, either positive, negative, or you can assign a sentiment score. In this case, it's going to be continuous, a number between minus 100% and plus 100%. Either completely negative sentiment or anywhere between minus 100 and 100. So in this case, so our target variable is really quantitative, numerical, or continuous. That's the same names for that variable. So people call it quantitative, numerical, continuous, target variable. Means the same. So in this case, our continuous target variable is in the range between minus 100% and plus 100%. So sentiment can be any number in that range. And first, as I said, you do manual labeling of the tweets. So you ask somebody, experts, to assign a sentiment score to each of the tweets. So for the first tweet, it's positive 56%, for the negative, negative 35%, and so on. And this becomes our target variable. Now we need to figure out, okay, so we want to predict the sentiment score for each new tweet that is coming in. For that, first we need to learn how we can model our target variable as a function of some features. So what are those features? That's the first question. So what are the features in the natural text? When we work with text, what are the features that we can extract from that text that help us to model its sentiment? Again, that's, in machine learning, that's pretty much the first question that you should ask. In some cases, it's obvious. So if you're going to work with images, so the features are the intensity of pixels. That's pretty much obvious. In natural text, not necessarily that obvious. But the standard approach to it, well, first, of course, what we may do, we may want to do the pre-processing of the text. So we may remove all stop words which do not have semantic meaning. And again, there's a choice whether we do it or not, but if we decide to do it, we can remove word home because it doesn't make any mean. We can remove are, was, our, that, did, that. So those are typical stop words that we remove. And we just stay with the words that have meaning. So where, T, love, that, and G. And now those words can become our features. But the question is, which information about these words can become a feature? So feature should be a number. The word itself is not a number. It's just a word. And there are a number of choices, but what typically people do, and again, we need to figure out which number associated with the word where we call feature x1, which number associated with word t we call feature x2, and so on. And the typical way is just the word frequency. So how many times this word where is found in the first field? Once. We put 1 here. How many times the word where found in the second field? 0 times. We put 0. How many times the word where found in the third field? Sorry, 2 times. And so on. So this is very, so the feature is the word frequency, WF. Can it be used as a feature? Potentially yes. Maybe there are some better ways, but at least there is something to start. So potentially the frequencies of the words can explain the sentiment. Now what we have, we have 5 examples, and we have features in every example. So feature x1 in example 1 is 1, in example 2 is 0, in example 3 is 2, and so on. We have our target variable, and what this data structure is typically called the bag of words in natural language processing terminology. And now all what remains to do is to figure out, okay, so which function, given these features, would produce a good values for the target variable for the sentiment score. And we have a bunch of possible functions that we can use over here in machine learning. Those are the typical ones that we will discuss in this course, and of course we'll start with linear regression. So in the case of linear regression, in general our function looks like this. So our function takes, in this case, 5 features as inputs, produces the output. And these theta are the parameters of the function. In the case of linear regression, those are just the coefficients of the linear regression function. And we need to compute those parameters from the examples. That's pretty much all what we do in machine learning, in supervised machine learning. So we have a target variable, we have features, we need to identify, of course, what are the good features that we can use to explain our target variable. And this is an open question, so this technology is typically called feature engineering. So we need to think and engineer some good features that have explanatory power to explain the target variable. In other contexts, those features may be called factors. Again, when we hear about factor models, pretty much the same stuff. In that case, x1, x2, x3, x1, x are called factors. But typically in machine learning terminology, features. In other application areas such as finance, those will be called factors. And after that, you have a choice of which function to use. So decision tree is a function. Linear regression is a function. Support vector machine is a function. Artificial neural net is a function. So, and as soon as you decide which function you are going to use, you need to compute the parameters of that function. In this case, it's the coefficients of linear regression. Those are known. How we do it? We compute those from examples. And how we'll see. And that's all what we essentially do in supervised machine learning. So we get our examples, in this case examples of tweets, we manually label the target variable. Again, if it's a picture, our target variable can be whether there is a cat or no cat on the image. In that case, somebody will need to look at all the images and label where is a cat or there is no cat. And we get the labels. Again, if this process can be automated, this is really great. If it's manual, this is costly. And again, people try to automate labeling of data for the machine learning problems. Of course, people use standard data sets as well, where everything is already labeled, and those data sets are publicly available for training your models. But otherwise, if you don't have access to a public data set that was already labeled, you need to essentially find an expert that will do the labeling for you. And there are special websites where you can whatever, where you can hire people and they will label, for instance, your sentiment or something else, or your images. And after that, you need to identify what are the features. Maybe you may need to do some feature engineering, engineer those features. And as soon as you have the features, you basically select which function you think is appropriate, and those are the typical choices. In supervised machine learning, we go through those. And after that, in order to use this function, you know that, okay, I need to know the parameters. I need to know these coefficients of my function that I selected. As soon as I'm able to compute those, when the new tweets come in, I know the coefficients, I know the features for the new tweet, and I can compute the target value. That's pretty much the full supervised machine learning life cycle. All what we do in supervised machine learning. The only difference is our target variable can have different meaning. Can be either discrete, in that case it's called a classification problem, or can be numerical, continuous, in that case it's typically called the regression problem. So you can have different features, different meaning of the features, different number of features. You may select different functions. Linear regression function and decision tree is represented as a function, you'll get that. And after that you need to compute the parameters of your functions. In the simplest case, coefficients of your function if it has a linear form. So this is all what we do in supervised machine learning. And as I said, it's important, that was important for us to understand these functions. Next step, of course, when we come to get deeper into linear regression, we need to figure out how do we compute those coefficients, those unknown coefficients. And that's what is called training of your machine learning algorithm. Computing these coefficients is called the training. When you take the neural net, you compute the coefficients of the neural net. We'll see those as well. When you do training for the linear regression, you compute coefficients of the linear regression function. When you do training for the decision trees, you compute the coefficients for the decision trees. You'll see those as well. So that's pretty much one slide, high-level overview of supervised machine learning. And again, everything in supervised machine learning works within this framework. Of course, your examples may not be text, maybe images, maybe something else, maybe stock prices, if you want to try it on that, maybe Bitcoin prices, maybe something else. Maybe your examples can be the crimes that happened historically in different parts of the city, and so on. You need to identify features, you need to do understanding of your problem, and after that you need to select your machine learning algorithm and you need to train. Okay, so that was an overview of essentially supervised machine learning. And now we can go into details of that. And that's where we spend probably most of this day today looking at regression models. Linear regression if our target variable is continuous, and logistic regression if our target variable is discrete. So yesterday we looked at this modeling process itself. I'll probably not spend too much time on discussing modeling in general. Model simplified representation of reality should capture the essence of the system without unnecessary details. Typically model tail for specific type of problems. They are still far from universal divisional intelligence. This is one of the important things to understand. So we do not have AI systems that are able to solve multiple problems at the same time, especially if those problems are from different domains. People are working on that. That's an active research area, designing AI algorithms that can solve different types of problems, but we are still far from that. We are still far from universal AI, where the Terminator will came, who can at the same time kill people and cook eggs and, I don't know, drink beer and so on. So multiple problems are not able to be solved by AI algorithms yet. So models help us to understand the work. There are different types of models. So optimization modeling that we'll see, predictions or regression models, clustering, and so on. Those answer different questions. For instance, optimization answers the question, what is the best? So prediction answers the question, what if? And clustering answers the question, how similar? So we'll see that. And of course, models are faster, easier, cheaper to experiment than the real system. That's a classical example of the Monte Carlo simulations that were designed, as we discussed yesterday, for the Manhattan Project for essentially experimenting with a nuclear reaction of the interactions between nuclear particles. And of course, it's much easier to run Monte Carlo simulations on the computer than to work with a real nuclear reaction, which is dangerous and costly. So that's that was our models and reality chart from yesterday. That's essentially the data scientist workflow. We have the problem. Based on the problem, we design a model, which is simplified abstraction of reality, but should capture the essence of the problem. After we design the model, we do the calculations. This, for instance, can be a regression model, linear regression, logistic regression. We do the calculations, we get the results. We need to interpret those results, we need to validate those results. And that part is probably, nobody can tell you what is a good way to validate your results. So for many problems, it's difficult to validate. Yeah, for some problems, yeah, if you work in computer vision, yeah, you know that. Okay, so the new images come in that has cat and no cat, and you can validate the results on those. But computer vision is just one of the domains. How you validate your results for the self-driving car that should be able to drive in different conditions, under different circumstances, and so on. So day, night, when it's snowing, how you validate your self-driving car in California if there is no snow in California. So all these validation things are really, really important. Validation, validation of results, testing of your results. And typically that's both science and art, how you do the validation of your results. And after you implement those in decisions, into practical decisions. Yeah, basically that's again another explanation of the modeling process. So constructing hypotheses, estimating the quality of the data source, that's what we did yesterday in statistics, quantifying the uncertainty around the data and predictions, like trying to identify hidden patterns from that information, understanding the limitations of the model, and in some cases trying to understand the mathematical proof and the logic behind the model. That's what we tried to do yesterday. So
quantify uncertainty, what does it mean?
So yesterday, when we talked about statistics, we quantified uncertainty around our data, confidence intervals. That's a quantification of uncertainty. For instance, we would also need to quantify uncertainty around our predictions in our model. So what is the error of the model? That's typically quantification of the uncertainty around predictions of the model.
Because it's range.
Yeah, and in data science, typically we are very simple. So we split our data set into training set and test set. So we train our model on the training data, and after we quantify its uncertainty around prediction of the test data. So again, that's a typical data science workflow, because otherwise doing whatever mathematical derivations of the uncertainties for the model is really difficult. So we try to do this training data, test data, and in many cases we also overlay it with cross-validation. So we'll talk about the cross-validation as well. As cross-validation, just reshuffling that training set and the test set a number of times in order to improve our estimation of the errors. Again, how do we do modeling for decision making? So need to get used to that. In these courses, very different type of models. Very different classification of models. People will identify for physical models, cars, buildings, engines. There are diagram models like decision trees or flowcharts. There are statistical models like probability distribution, mathematical models with like scheduling, Monte Carlo simulations, other computational models such as neural nets. There are multiple classifications of the model types. In this course, we'll typically classify models into statistical models, such as hypothesis testing, for instance, t-test, into optimization models, simulation models, and machine learning models. Even so, this is slightly different slightly different classification that I would like to typically use. Again, 7 steps of modeling process. Define the problem, observe the system and collect the data, formulate the model, which is both art and craft, verify, run the model, and after verify, validate model results. Use model to help select among alternatives, presents results to decision makers, and implement solution. And again, this is also a very important part in many cases that we neglect. Present results to decision makers. So there is somebody who will take the decision whether to put your model into practice or not. That can be your client, your boss, your colleague, yourself, whatever, the government of Canada, government of Ukraine, or whoever else. So, and that is an important part. So based on our modeling, we should be able to tell a story. So storytelling is a very important component of data analytics and AI, to be able to tell the story based on the data. So to be able to do presentations, to be able to validate the results, to be able to visualize the results, so that we can explain what's going on to a decision maker. Yeah, that's another process, let's skip that. Okay, so linear regression. So some people will tell you that linear regression is a statistical algorithm, some other people will tell you that linear regression is data science algorithm, other people will tell you that linear regression is machine learning algorithm. And all of those people will be correct. And you know, if you're coming from a statistical background, you would call some of the things that we do in linear regression different way than if you're coming from the machine learning data science perspective. That's why we first look at linear regression from a statistical perspective, and after that we'll look in more details into linear regression from the machine learning perspective. Even so, the formulas are the same, just people tend to call things differently in statistics and in machine learning. And again, machine learning is something relatively recent. The last 10 years, statistics comes from 100 years. So that's why, of course, statisticians had worked these regression models for years, and they have their own way to call things. So how we look at regression, linear regression from the statistical perspective. So what we did in statistics yesterday. So we defined the population, and after, as we typically cannot have access to the whole population, we had to do sampling, we had to collect our sample. For instance, we had to poll our people who vote, and because we cannot ask everybody in the population about whom we are going to vote for, we had to select a sample, for instance, 1,000 people, and collect the data of those, do the polling. After that, we did the descriptive statistics. We computed these one-number summaries, mean, standard deviation, median, percentiles, and so on. We looked at our data. That's called descriptive statistics. We looked at the bar plots and so on. On the top of that, we did the hypothesis testing. There's a hypothesis. On the top of that, we didn't really touch that much. We should be looking at correlations as well. If we want to identify how related is our data to each other. And on the top of that, we can do the regression. So, an example. What is a regression? So this is one of the examples that people tend to use. And the question that we are trying to answer, how is Uber fare calculated? And if you know really all these steps, how it's calculated, you have no issue. So for instance, that's for Toronto, but of course for other cities it's similar. So when you just sit in a cab and basically you already need to pay $3.25. After that, your fare increases with each additional 143 meters at 25 cents. So for each 143 meters that the cab drives, you pay 25 cents. After that, you're paying 25 cents for each additional 29 seconds of the taxi being idle, standing on a traffic light or somewhere else. And you pay $2 for each passenger in excess of 4. So if there are more than 4 passengers, you pay $2 additional per each passenger. For the 5th passenger, for the 6th passenger, and so on. It's all good if you know these numbers. You can calculate the fare in the taxi. So, for instance, that's essentially the formula, the constant, $3.25 plus 25 cents per this unit of distance plus 25 cents per unit of idle time plus 2 multiplied by the number of passengers in excess of 4. So if you have this trip, 3 people, 6 kilometers, 4 minutes of the idle time, you can put this into the formula and compute that the fare was 15 bucks and 80 cents. So this is all good. But what happens if essentially you do not really know these things? How much you pay for the unit of distance, how much you pay for the unit of idle time, and so on and so forth. All what you have examples. This fare was paid for the distance of 6 kilometers, for this idle time, and for this number of passengers in excess of 4. In that case, essentially, what we can do, we can infer these unknown coefficients, or how much we pay per unit of distance, how much we pay per unit of time, how much we pay for the number of passengers in excess of 4, from these data points, from these rides that have been already taken. And what we do in that case, we denote this as a variable y. This is called the dependent variable in statistical terminology. We denote the distance by x1. This is called the independent variable x1 in statistical terminology, independent variable x2, independent variable x3. And after we write down this equation that says our independent variable y is equal to the coefficient b0, which in statistical terminology is called the intercept, plus the coefficient b1 multiplied by the dependent variable x1, and b1 is called slope, b1, b2, and so on are called slope of the dependent variable x1, plus b2 multiplied by x2, plus b3 multiplied by x3, plus the error term epsilon.
Sorry, you said dependent. I think it's independent x1, x2.
Yeah, that's right. So independent, dependent. We also, yeah, that's right. It's when you talk and think at the same time, it creates many sort of inconsistencies in the speech. So, and after that, when we look again at the regression statistical perspective, we use pretty much our knowledge of statistics. So we use p-values to figure out whether each coefficient is statistically significant or not in the regression. So whether this is statistically significant, this is significant, this is. Those are the same p-values that we used yesterday. Essentially, linear regression is the hypothesis testing, in a sense. Can be considered that way, and we'll come to that illustration. So that's why it's a decision called statistical algorithm. That's hypothesis testing, and you test which of these features in machine learning terminology or independent variables in statistical terminology are statistically significant or not. And that's why when you see the results of the linear regression, you have the p-values. You can also have the t-statistics, the same t-numbers that we have seen yesterday in the statistics course. You also see something else which is called f-test. So f-values are the joint importance of all coefficients together. P-values are importance of each coefficient individually. F-values are the same as p-values, but joint statistical importance of all coefficients of linear regression together. That's what is called f-statistics. So R-squared will come to R-squared. So R-squared is the goodness of fit, and it's one of the measures of how good is your predictions of your regression. Even so, it's a bit misleading, and in my opinion, we should use mean squared error mostly instead of R-squared. But we'll come to that. So, as I said, from statistical perspective, linear regression is the hypothesis testing. And let's say we have only one independent variable, x1, so we have only one coefficient beta1 for simplicity. So our new hypothesis in linear regression in that case is there is no linear relationship exists between independent variable x and dependent variable y. In our terminology, the coefficient beta1 is equal to 0. No linear relationship, beta1 is equal to 0. Alternative hypothesis is consequently beta1 is not equal to 0. So there are different possible data that basically we can test. And let's look at just these 4 cases. This is one possible data set where we can test this hypothesis, another data set C, and data set D. So as you see here, so if we fit a line to this data, so the slope of that line is 0. As a result, beta 1 is 0. That's why it's called the slope. It's essentially the same interpretation as in our review of kinetic. The slope of this line is 0. As a result, the angle alpha is 0, tan of alpha is 0, whatever, coefficient beta 1 is 0. So that's why it's called the slope. And in this case, what we do, in case A, no linear relationship exists. So we are not able to reject null hypothesis, we are accepting null hypothesis in other terminology. And for that, we look at the same numbers as we used in our statistical hypothesis testing. So this is the region where we are not rejecting our null hypothesis. Here is the 2 regions where we rejected our null hypothesis. Again, typically we have the threshold of the p-values of 5%. That corresponds to 1.96 standard deviations in each direction from this. All the same interpretation as we had yesterday for statistical hypothesis testing. Just it's now applied to the coefficient of the linear regression, this hypothesis. So, there are some other cases. Like this case is basically what you should do. So, linear relationship is not enough. You should look at potentially fitting a non-linear curve to this data. So here, this is really a good case. Linear relationship exists and we are rejecting null hypothesis. Beta 1 is not 0. This line is not horizontal. So we are rejecting null hypothesis. And here again, so we need to look at the higher order relationship because linear fit may not be good enough. Okay, statistical perspective. Another thing that covered in pretty much many statistical courses when we talk about the regression is how about the errors? So when we look at our regression line, so there is an error curve. There is something that we cannot explain with the help of our variables. And that's true in machine learning as well. In most cases, there is some error that we cannot explain. That's a typical case. There is still some error that we cannot explain. And in linear regression, so that error term, epsilon, is assumed to follow a normal distribution. That's a property of linear regression, which we often ignore in data science. But we don't ignore it in econometrics, in statistics. Pretty much econometrics is mostly about linear regression and other cases when something goes wrong. So what do we do when the random error term is not normally secret? How do we fix that? And I think it's called what, heteroscedasticity? Yeah, something like that. Heteroscedasticity problem, and you spend in basically a bunch of techniques how to fix that issue. But in data science, we typically don't worry too much about that. So we are in many cases we are just ignoring these type of assumptions. As soon as it works and we can validate the results from our test set, we put them all into production instead of going and necessarily fixing all the statistical misconceptions in linear regression or any other algorithm. So what that means that the errors are normally distributed with, of course, zero mean and constant standard deviation sigma. So what it means for every point here, the errors are normally distributed with the same, with zero mean, of course, the mean is 0, and with the constant standard deviation. So standard deviation doesn't change. For this point, it's the same standard deviation of the errors sigma than for this point on the regression line. So those are the assumptions.
And the error is the distance between actual point and expected or model point.
Yeah. So that's error. So this is our actual point in the data set, and this is our regression line. So this is the error. We still, again, we'll talk more about it, or how we measure this error, but the error is really proportional to this distance. Can be square distance, can be just the absolute value of this. So in linear regression, this is the square. This square of this distance, that's why it's called ordinal least squares. Method I mentioned for that. So that's what it is. So this is the error. Okay, so that's basically how we operate the result. So in this case, so distribution of y at x equal to 65. So here is x equal to 65. So the mean is beta 0 plus beta 1 multiplied by 65, and standard deviation is sigma, and the standard deviation is constant. So this is the mean itself. Of course, the mean of the error is 0, and this is the mean of the variable y. The mean of the error is 0, and the standard deviation of the error doesn't change. It's always sigma for any point on the regression line. How regression is used in statistics and econometrics. So that's a traditional use of statistics, of regression statistics econometrics is essentially they test many interesting hypotheses. The one that I like, and it's for instance described in this book, which is called Beauty Case, basically they test the hypothesis on a bunch of data sets whether people who look beautiful are more successful in life, or it's why attractive people are more successful. And they use a bunch of the data sets and they really show yes. According to this regression analysis, attractive people are more successful in life. And one of the examples that we use is do good looking professors get higher teaching evaluations. So basically this book is written based on a collection of papers, on academic papers, and one of those is looking at teaching evaluation of professors. Another where they did some analysis of the workplaces and stuff like that. And what they conclude using linear regression? Yes. Good-looking professors have high teaching evaluations. That's what they conclude by using data sets from teaching evaluations. That's typical use of linear regression in economics. These two books, if you read Freakonomics and Super Freakonomics, anybody who read? These two, all based on linear regression, pretty much. All the interesting facts that they discover in those books, relation of crime rate to I forgot what, it's all linear regressions. They just phrase it in a nice way, so they really found some interesting data sets, they really found some interesting hypotheses to test, they used linear regression to do it, and after that they put it in these two books and they nicely describe what's going on. But the underlying algorithm is linear regression, pretty much. That's an interesting thing. So New York Times bestsellers are based on linear regression. And for us,
in the example of beauty, so can you just briefly describe how they use a linear regression, comparing that it pays off? So for why they take what?
So your target variable is the teaching evaluations, the score that you get on teaching evaluation. And here they have, as their independent variables, they put some measure of attraction. They put some other factors, whether you are full professor or part-time professor. So they basically design a number of independent variables that can explain the teaching evaluation. So there are some standard ones, but one of those variables is the beautifulness. So they include the I forgot how they measured it, but I put some measure of attractiveness of a professor, how that professor looks like. Of course, we include other things. We should account for gender of the professor. We should account for whether the professor is full-time or not. We should account for the years of experience of that professor, because there are some other variables that can explain essentially the high teaching evaluations. But what they essentially have gotten, they gotten that variable for the attractiveness is statistically significant. That's basically the conclusion that they made.
But in that book, I mean, the beauty is the perception of beauty in different cultures and countries is different.
Yeah.
What we might find beautiful, Chinese might not, and vice versa.
That's right. They mostly did it for the US, but I think they discussed that as well. So we discussed as well, of course, very different perceptions of beauty and so on and so forth. So this is mostly based on the US data.
But is this causation or correlation?
Well, they basically show this is causation. And they put some arguments that, yeah, that's really the case. It's not only the correlation that they found significant for attractiveness, but there is that's basically the purpose of the book. That they basically try to convince people that, yeah, there is a causation effect. Even so, it's difficult. So, yeah, you have a correlation in your linear regression. Your coefficient is significant. Now you need to figure out, can you explain the causation?
So basically, if you use a statistical surgery, you increase your chances.
Potentially, yeah, but you need to prove it by the data. Maybe if you do this surgery, and in that case it doesn't work, maybe you should be naturally beautiful. I know. That's something that they didn't test, as I understand. So that's why, yeah, in that case, they probably didn't have enough people who did their surgery in the data set, so to make any conclusions. So,
but probably it makes sense to invest in surgery to increase your bonus for lectures.
Yeah. Cool. We should take a break now. Yes. Okay, that's a good break point. So we ended up this statistical perspective on data science, but on statistical perspective on linear regression. So this is really, that's pretty much what most economists are doing, or econometricians, whatever we call them. So they use such tools as linear regression to really show that something, and that can be, yeah, if you want to design a policy change in the country or something else, you basically run your linear regression and try to see how that policy will be influenced by your variables x1, x2, and so on and so forth. So what you will get. So most of economic research, as I understand it, and Katerina can correct me if I'm wrong, is based on regression. Now that's what it is. Okay, any other questions before we take a break? Okay, the break. Now there are some things
Thank you very much.
and for you. Let's continue. So we talked about linear regression from statistical perspective. Now we'll briefly talk about linear regression from data science perspective, and that from the machine learning perspective. Again, so essentially in linear regression we are trying to build a linear trend in our data, and basically usage of linear regression, there is twofold usage. So in most cases we will be really interested in these coefficients, which tell us how important are our features in the data, but in many other cases we will be just interested on the question, do we have a strong relationship between our target variable y and our feature xi? And that's the second use case, which in many cases is kind of neglected, is often used in medicine. So for instance, to answer the question, did the patient who received treatment show statistically significant improvement versus patient receiving a placebo? In this case, we're often interested what is this coefficient beta between the treatment and the response of a patient, but what we listen if this relationship is statistically significant, if this correlation is statistically significant. We're not going to use the coefficient itself, we just need to answer this question. Is this statistically significant or not? If yes, so the medication works. If not, the medication doesn't work. That's kind of the second use case where we just want answer to that question. Or what is the biggest driver in customer response? TV advertising, banner, direct mail, email. Again, we are not going to be using coefficients, we just want to find the most important driver in the advertising response. Of course, typically, as we said, we are going to be really interested not whether the relationship is strong or not. We would be interested in the function itself, in the linear regression function, in the coefficients. Okay, so now let's look at an example of a data set. So, can we predict the CO2 emission of a car without testing? And that's what we will try to do. So, We have historical data about the past cars, including number of cylinders, engine size, consumption, and of course our target variable CO2 emission. So we want to build a linear regression model, and after that, when the new car comes in, so we would like to predict the expected CO2 emission for the new car. Again, this data set is in Python, but let's look at our standard notation that we will be using for this course. So what we have? We have our features, number of cylinders, engine size, consumption of fuel, and so on, and we have our target variable, CO2 emissions. So target variable we typically denote as y, and y2 means target variable in the second example, so second row. So this is the first example of a car, second example of a car, and so on. So here, this notation means that's the second feature, engine size, second column, and the first row, example number 1. Here, for instance, is x13, so feature number 1, number of cylinders, example number 3, row number 3, 1, 2, 3. That's our notation. So what we'll typically do, we'll split our data into a training set that we'll use to compute the coefficients of our linear regression model, and the test set that we'll use to evaluate the error of our model. And after that, of course, we have the prediction set, so when the new data comes in for the car, we know our features, but we don't know, of course, the amount of emission. We plug in these features into our linear regression model, and we have our prediction. So that's a standard setup that we'll have pretty much for all supervised machine learning problems. So columns typically represent our features, rows typically represent the examples, y is the target variable, x1, x2, x3, and so on are the features. And examples are denoted as a superscript, features are denoted as a subscript. Let's actually start with this. So this is probably the most important picture for this lecture, because now we'll put together everything that we knew from our review of mathematics from yesterday, and we look in details into our machine learning algorithm. So what we said, so in linear regression, so we are going to be using the linear regression function. In this case, the function looks very simple. There is only one feature, engine size, and the target variable CO2 emissions. Again, typically we have much more features than one, but to illustrate what's going on, one feature is more than enough. X. So in this case, so our function looks like beta 0 plus beta 1 multiplied by x. So that's how function looks like, and beta is a vector of unknown coefficients. In this case, has two coordinates, beta 0, beta 1. So that's a vector of unknown coefficients, which in machine learning terminology are called the parameters of linear regression, and we would like to compute those parameters. So we have the functional form of our machine learning model. One feature, we have for it a number of examples, example 1, example 2, and so on. And we want to compute these unknown coefficients of linear regression, the parameters of our model. The question is, for that, we touched yesterday, we need to somehow to define what is the error of the model, and after minimizing. So the next step would be, we have our function, which in machine learning terminology is called hypothesis function, that's a linear regression function, but we also need an error function. The function that defines an error in our predictions. How we can define an error? So let's look visually. So this is example number 1. So in example 1, this is, so x1 is the engine size, and this is the y1 is the amount of CO2 emissions. When we fit a line, and we still don't know which line is there, we still don't know the coefficient beta 0, beta 1, there is an infinite number of possible lines. What we have, so this distance will define an error, for example 1. But we still need to write down in terms of formulas what is this error. We know that, yeah, of course, the bigger this distance, the higher is the error. For example 1. In example 2, this is the error. So in example 1, that's what we have in the data, that's what our model predicts. Our model predicts like that. Our data has 1. Or 1. In example 1, that's why we have 1. So this distance is there. But now how do we write down that error? So yesterday we discussed two possibilities. So what we can do to define error in example 1, we subtract this from this, but again, subtracting is not giving us the error because it can be negative, it can be positive. What we need to do, we have two possibilities, either to square this or to take absolute value of this, yeah? So now in this case, that's going to be a positive number. This is going to be a positive number that defines an error. If these two variables are the same, the error is 0, as expected. If they are different, there is a distance. In that case, the error is a positive number. So this is really defining an error. This is really defining an error. Everybody with me so far? Again, this is one of the most important concepts. We are trying to design the error function based on our hypothesis function. Everybody with me so far? How about example 2? Now, what is an error in example 2? Well, the same as here. So, example 2, what we have in the data target variable and what our model predicts, or the absolute value. So that's an error in example 1, that's an error in example 2. What is the overall error? Well, we can just sum up errors in all examples, and that's an overall error of the model. Or let's say here. Again, everybody with me so far? So next, what we want to do, well, we want to minimize an error. So we will need to solve a minimization problem of this form to compute the unknown coefficients of our linear regression. That's what we will need to do. And as we discussed yesterday, we also need to think about the properties of these functions. So this is a quadratic function, this is an absolute value function. Then we are minimizing which properties we want this function to satisfy, to be satisfied. Yeah? Yesterday we wrote 3 properties. 1, continuity, 2, differentiability, and 3, convexity. So, how about this function? Is it continuous, differentiable, convex? Yes, no? How do we check that?
That's in English.
Okay, let's do it first. So first, instead of point 1, we need to substitute our hypothesis function, yeah, which is linear function. So instead of point 1, we substitute beta 0 plus beta 1 multiplied by x1 over here. Everybody with me? That's our prediction. So we need to substitute the function that is representing our model before we make any conclusions about convexity, differentiability, because it all also depends on this, which function is that. In this case, it's very easy linear function. So, and we can rewrite this as, in that case, y1, which is just a number in our data set, minus beta 0 plus beta 1 multiplied by x1 squared plus the same for. And we need to remember that the unknowns here are beta 0, beta 1. So we'll be minimizing this function with respect to beta 0, beta 1. Those are our unknowns. That's what we want to compute by minimizing this error function. Now, when we look at this function in terms of the unknowns beta 0, beta 1, what is that function? Is it continuous, differentiable, convex, or not? Now let's get to the discussion.
Continuous.
Oh, what we do? We take, that's linear function, we take it squared.
Yeah.
No? That's a quadratic function, yeah?
Yes.
Is quadratic function continuous?
Yes.
Yes. Is it everywhere differentiable?
Yes.
Yes. Is it convex?
Okay, so we need to check.
We need to check. Quadratic function can be convex or not. So this quadratic function is convex. This quadratic function, which is minus x squared, is not convex. Everybody with me? So, in this case, it will be easier. All what we need to do, we need to look at the coefficient in front of the quadratic function. Whether it's positive or negative. What we have here? +1, yeah?
Yeah.
Everywhere. So, that's going to be convex quadratic function, because the coefficient in terms of the quadratic function, this coefficient is positive. Yeah, so what we do, this is linear function, in beta 0, beta 1, we take quadratic function of the linear function, that's it. And we can use some of the properties that we discussed yesterday to check the convexity. So what we basically said, if function f is convex, that's one of the properties, the affine transformation of the domain ax plus b is also going to be convex. So, in other terms, in our terminology, if function f of x is convex, the function, okay, and our variable is beta, so that's, so the function beta 0 plus beta 1 multiplied by x is also going to be convex. Yeah, so this function is quadratic, convex quadratic, this function is essentially beta squared. So, positive coefficient in front of it, we can compute the Hessian, which is 2. Hessian is, so the second derivative of this function is equal to 2, which is strictly positive. So this is convex function, affine transformation of its domain is also convex function. So we use properties of the convex functions from yesterday to basically show that this error function, which is also in machine learning called the cost function or the loss function, is a convex function. So that's why when we minimize it, to compute the unknown beta 0, beta 1, everything is nice. Yeah, it's going to be a unique global minimum. Those coefficients beta 0, beta 1 are going to be unique. We don't have any problems with local optimas, so we can easily solve this optimization problem. And that's what we'll do as well. But before we go to solve, this is pretty much the illustration how you write down the error function from the visualization. And of course, we need to minimize it. One thing to distinguish, we work with two functions. So this function is typically called the hypothesis function, that's a linear regression function, but we also need to write down the error function, representing the error of our machine learning model. And to do that, we need to figure out what is the error, or the error is the difference between our target variable in example 1 and what our model predicts. This is point on the line, which we call y hat. And now we need to sum up errors for all examples. So example 2, example 3, example 4, and so on and so forth. So we need to sum up all these errors. So this error for example 1, plus error for example 2, plus error for example 3. But because we know that this is a convex function, this is a convex function, some of the convex function is also going to be convex. Again, very easy in this case to show convexity, and we know that very nice properties of the function that we are minimizing, we can easily find its minimum, which we will do as well later on. But for now, that's the procedure that we will use pretty much for all supervised machine learning models. We'll need to identify the form of the hypothesis function. After it, we'll need to figure out which of the error functions make sense to use. This one, which is typically called MSE, mean square error. This is called MAE, mean absolute error. And there is one more that we'll see later, log loss. But for now, let's ignore that. This is the most typical and mostly used. And because of the same things as we just discussed. So for linear function represented by hat, it's convex, very differentiable and continuous, of course. So mean absolute error used sometimes. There is a regression which is called mean absolute error regression, not used that often because of a couple of things. So it's non-differentiable function, and you need to deal with that. Even so, there are ways to deal with that, and it's not typically, and that's actually discussed the second reason. So why do you think, except for non-differentiability that we can correct, why do you think the mean squared error is more popular than mean absolute error? What you can tell the difference between this error and this error. When we square a number and then we take the absolute value of the number, what is the difference?
Size.
Size. Exactly. When we square a number, this becomes much bigger than the absolute value of the same number. What does it tell us? This function will penalize large deviations, like this, from the model much bigger than this function, because we square the deviations, yeah? And the squared number is much bigger than the number itself, than this one. Typically that's beneficial. It will penalize these outliers with much bigger weight than the mean absolute error. That's another advantage why people use mean squared error instead of mean absolute error. So you would like to penalize these large deviations.
It's progressive.
Then with much bigger weight than small deviations. Probably small deviations do not matter. Who cares about this small deviation? Small error in the model. But yeah, if you have a large deviation like this, we would like to penalize this by much more. And again, essentially what we are doing by minimizing this function, we computing the optimal coefficients beta 0, beta 1 that give us the optimal line. So because there is many possible lines, we are basically finding the line which has the best error, which has the smallest error, minimal error in the other terms. That's all what we are doing. We are minimizing the error of our model in order to compute the unknown coefficients, parameters, beta 0, beta 1. And that's going to be the same for other machine learning models. Just of course the function will be different, but the principle is going to be the same. We select the function, the hypothesis function, after that we decide which of the error functions we use, and we minimize the error function. That's it. And by that we compute the parameters, unknown parameters of our model, in this case unknown coefficients beta 0, beta 1. So we are computing the vector of unknowns beta. That has two coordinates in this case. Yeah, in many cases beta 0 is called the intercept, beta 1 is called the slope. Why? Because, so what is beta 0? Beta 0 is this intercept, where it intercepts the vertical axis, and beta 1 is the slope. Yeah, beta 1 is the slope. That's all what it means. Yeah, knuckle and Pareto in Ukrainian, yes? Again, all these small things should help you to understand this in more details. There are many small things inside this model, but at the end, because we will get back to these derivations for other models, for logistic regression, for decision trees, for neural nets, we'll go to the same procedure. So that should become basically a picture in your head. In machine learning, it's all the same. Procedure is the same. So you select the function that you think is a good model. People will call the hypothesis function. In our simplest case, in the linear regression, it's just simple linear function. But it may not be the best function. Maybe decision tree function is better for that particular data set. Or maybe neural net is even better. After that, as soon as you select the function that you're going to work with, there will be some unknown parameters of the model. Typical coefficients of the model. In this case, beta 0, beta 1, that you need to compute from your examples that you have. In order to do that, you formulate the error function, which is just the difference between your target variable in every example that you have in your data and the predictions issued by this function, by this model, which we typically call y hat. We typically square the error, we typically use mean squared error, and after that we need to minimize this function with respect to the unknown coefficients, with respect to the unknown parameters. How we solve this minimization problem? We use one of our favorite optimization algorithms, and we discussed three yesterday. That's what we'll do next. Quasi-Newton of gradient descent. And because we know the properties of our error function, in this case very nice properties, we know that we'll find unique global minimum. And in this case it's very simple because our function is convex quadratic. For convex quadratic we can actually, well, let's get to that, but for convex quadratic we can easily find the minimum. Anybody remember this? So that's going to be the point of minimum because we know that our function is convex quadratic. All that we need, gradient of our function with respect to unknown beta is equal to 0. Or we can use one of the three optimization algorithms, but because it's a quadratic function, there is a trick. Gradient is equal to 0. What is the gradient of quadratic function? Linear. So this is a system of linear equations that we need to solve in order to find the coefficients beta 0, beta 1. That's the standard algorithm for solving the linear regression problem. It happens, we are lucky that the gradient happens to be linear function. Gradient derivative of quadratic function is linear, and this is going to be just a system of linear equations. In this case, it's two unknowns, beta 0, beta 1, two equations, two unknowns, very small system. Yeah, so now we are starting to use all this machinery that we discussed yesterday from mathematics, statistics, algorithms to be able to do machine learning. Okay, so now let's, so we'll come back to the things, but now let's write all this down formally. And after we'll get back to some of the interesting tricks in linear regression. So, in 3 slides, we'll write down everything formally for linear regression. Oops. Okay, our annotation, just probably repeat it. So what are the input? Those are the features. We have n features, and xij is the value of the feature I in the j's training example. Again, annotation is complex, but what can we do? xi is feature I, and j is the example done by j. We have n features and examples. So if you put features as vector, it's x0, x1, x2, and up to xn. And there is a trick that we typically say, basically to be able to model the intercept, we set x0 feature to be equal to 1. So 1 multiplying the first coefficient gives us just the first coefficient. Next, we write down the hypothesis function. In many cases, people call it h, just to represent hypothesis function, so here I call it f. And again, machine learning, people typically call the coefficient theta instead of beta. Again, matter of notation. So in linear regression, historically we call those betas. Now, when machine learning was extended to other functions, like logistic regression, we typically call those unknown coefficients theta. So this is the form of the hypothesis function. Theta 0 multiplied by 1, we just normalize feature x0 to 1 in this vector. Theta 0 plus theta 1 multiplied by x1 plus theta 2 multiplied by x2, and so on and so forth, plus theta n multiplied by xn. And we can write this down in the vector matrix form, as we would always do. So the vector of the coefficient theta transpose multiplied by the vector x. Again, this is the linear function written in the vector matrix form. Nothing more than that. Vector theta transpose multiplied by the vector x. Dot product.
You can remind once again what is transpose matrix.
So, for the vectors it's even easier. So theta is the column vector. Let's just write it down. Let's do the vector first and after the matrix for transpose. So theta, when we define the vector, it's a column vector. Yeah? Now, when we transpose the column vector, it just becomes a row vector. So nothing more than that. Beta 0, theta n. That's a row vector. Yeah? So x is also a column vector. Yeah, that's just 1, that's 1, and 7. Now, theta transpose multiplied by x. So this theta transpose, this is x. When we do the multiplication, we do this. Yeah, everybody remembers. So the multiplication is equal to theta 0 multiplied by 1 plus theta 1 multiplied by x1 plus and so on theta n multiplied by xn.
And what if we would multiply vector and vector?
So again, when we multiply two matrices in general, the inner dimensionality of the matrices should coincide. Yeah? So in this case, the dimensionality of theta transpose is 1 by n. By n plus 1, because we start with 0. The dimensionality of x is what? N plus 1 multiplied by 1. The inner dimensionality, in both cases n plus 1, we can multiply those. So we can only multiply matrices when the inner dimensionality coincides.
Why don't we multiply vector and vector?
Oh, that's what we do, multiply vector and vector. But in order to be able to multiply these two vectors, the inner dimensionality, the second dimension of the first vector should be the same as the first dimension of the second vector. That's why we have to transpose it. Because otherwise, this vector has dimensionality n plus 1, 1. And as you see, this inner dimensionality is 1, this inner dimensionality is n plus 1. We cannot multiply theta with x. We have to transpose theta first in order to be able to multiply this.
Это просто правило умножения матриц векторов. Одно должно быть вертикально, другое горизонтально.
Разрядность матрицу.
And in general, when you want to multiply two matrices, so A multiplied by B, so let's say this is M multiplied by M, and this should be M multiplied by Q. So the inner dimensionality should be the same, and after we can do the multiplication according to the rules of multiplying two matrices.
And as a result, we receive n by k matrix.
Yeah, and we receive the resulting matrix will have n by k, so they have the outer dimensionality. Again, I just review only one formula for multiplying two matrices. And because vectors are also matrices, so it's going to be the same. Just Google it, and for myself, I tend to remember that we need to know how to do the multiplication with that razor. Okay, let's do an example. So let's do the multiplication of 4, 6, 1, 2, and we want to multiply it by 1, 2. So how do the multiplication of this? Matrix by vector. So what you do, you take this, overlay over this, and to get the first coordinate is going to be 1 multiplied by 4 plus 2 multiplied by 6. 1 multiplied by 4 plus 2 multiplied by 6. So you do this, you overlay it over this. 1, so here you have 1 and here you have 2. 1 multiplied by 4 plus 2 multiplied by 6. After that, you do the same for the second coordinate. 1 multiplied by 1 plus 2 multiplied by 2. 1 multiplied by 1 plus 2 multiplied by 2. That's it, and you got your result. Here it's 12 plus 4, 16. And here is 1 plus 4, 5. So the resulting is, the vector 16, 5. Probably during the consultations, if there is necessary to review matrix vector multiplication operations, so you can do it. There is nothing, the only operation that you need to know is multiplication of two matrices. Because addition of two matrices happens element-wise. There is nothing, the same subtraction, there is nothing difficult. The only operation that doesn't happen element-wise is multiplication. Of course, division as well, but division can be represented as multiplication. And because, we work with high dimensionalities, nobody is going to write this as a scalar because the number of features may be millions. So nobody is going to write all these models in the scalar form. It just takes forever. So every body will write those in the vector or matrix form. And that's a matter of convenience. Again, it's useful to know that, this and these are the same, but this is just a long mutation that nobody is going to use. That's what it is. So this function is a linear function, and it's written as the vector of the coefficient theta transpose multiplied by the vector of the features x. And by default, vectors are column vectors, not row vectors. When we transpose, we get the row. When we want to transpose the matrix, so what we do, we just flip it over the main vector. That's a transposition operation for the matrix. The same for the vector transpose of the column is the row, and transpose of the row is the column vector. So we easily still flip it along the main diagonal, but because the main diagonal is the first element, so that's this type of flip. Okay, any other questions? Okay, now, these unknown coefficients in this hypothesis function are called the parameters in general, or coefficients, parameters, the same meaning. So theta is a vector of unknown parameters for this function that we need to compute. We don't know those yet. In order to compute those parameters, we need to formulate the error function, which in many cases is called the cost function or the loss function. What that function is doing, that's a function of these unknown parameters, and in our case, because it's a mean squared error, in our case, what we do, that's a difference between the hypothesis function by hat and our target variable. We have the example, so we square this and we sum up over examples from 1 to n. And if we want, we can make it the average error. Divide by the number of examples, these two typically there, because when we take the derivative, 2 by 2 will cancel out, and in the gradient we will not have to. But again, this doesn't really matter. Just when we multiply convex function by a positive number, it's still a convex function, so the optimal solution will not change. And after that, we minimize this cost function with respect to the unknown vector theta using one of our favorite algorithms, which is here. So now we have two choices. Either use our favorite algorithm, Newton, quasi-Newton gradient descent, to minimize this function, or what we may notice that because this function is quadratic, convex, and Riemann differentiable, and the gradient of the linear function in the optimum should be equal to 0, the gradient of the quadratic function is linear function, so we get this as a system of linear equations. That's all. That's another trick. So that happens just because our function is quadratic. If our function was non-linear in general, it wouldn't work, because this will be a system of non-linear equations, and in that case we need to go to one of the algorithms. In any case. For linear regression, we have choice. Use the optimization algorithm, one of the three that we discussed, or notice that the system of these non-linear equations actually happens to be a system of linear equations that we can just solve in one shot without using any of the optimization algorithms. This is typically solved the system of normal equations, or linear equations. As we need to be able to compute the gradient, in any case, we have to formulate the system or for one of our optimization algorithms, so it makes sense to write down the gradient vector. That's what we did yesterday. We need to differentiate our cost function with respect to each of the variables theta 0, theta 1, theta 2, and so on. And because this hypothesis function is the linear function in the thetas, so that's going to be the derivative. So derivative of the quadratic function with respect to thetas. So what we have here, we have so we have 2 multiplied by the function itself. That's a now linear function. There is no square, and now we need to differentiate this according to the chain rule. So with respect to theta, and of course we have x as derivative of that. So we can do that on the board. So this differentiation to be able to compute the gradient. Just simplifying. So what we have, we have function theta transpose multiplied by x. I just got to simplify notation. Now we need to compute this derivative with respect to the vector theta. Yeah? What we do, it's the chain rule. So this quadratic function, its derivative is going to be 2 multiplied by this function itself. Now we need to multiply it by the derivative of this term with respect to theta, which is happen to be x. So that's all what we do for the derivative, and that's what we get in our more complex notation. And because we have we have 2 in our loss function, 2 and 2 will cancel out, and we don't have 2 anymore.
What is 1 divided by m?
Yeah, so 1 divided by m doesn't matter either. So you can keep it there, you can remove it there. It's just the constant in front of every every gradient.
Why it's added here?
Why it's not here?
No, why it's solving normal equations? Yes, this 1 divided by m. So why it's there? So
Just to have average.
Why it's there? Well, yeah, doesn't matter. it's easier to interpret the error as a mean squared error, and because it's a mean, we divide by n, by the number of examples. At the end, this term doesn't change the solution when we minimize this function. Just any positive number in front of the function you minimize is not going to change the optimal solution theta. But because we want to interpret this as a mean squared error, we divide by n.
And why we have chosen 1 divided by 2?
Again, 2 is a matter of convenience. When you take the derivative, 2 will cancel out. Again, just the gradient will not have 2 in this case. At the end also doesn't matter.
Okay.
Because the solution is not going to be influenced by this.
Okay, it's just for convenience.
Just for convenience. People just keep it there to even so probably without it it's going to be easier to see. But if you really want to interpret this as a mean squared error, that's what you need to do. You need to divide by n, but you don't need to remove to be precise, because that's mean squared error. So here I didn't try it correctly because we need to divide by the number of examples and so on. Again. Okay, now, so what we want to do, we want to rewrite this as a system of linear equations written in these forms. Now we want to rewrite it in the matrix and vector form. So what we do, we leave this on the left hand side, we have our unknown, and we move this to the right side. So essentially having this system of linear equations, and this represent each equation from 1 to n. So that's the first equation. So that's the left hand side of the equation because unknowns are collected there. This is the right hand side of the equation. So the vector of the constant numbers, and we have n equations. What people tend to do, they tend to introduce this big matrix X and this vector Y. So the vector Y contains Y's target tables in each of the examples from 1 to n. The big matrix contains the column of ones, and after that here is x11 is the teacher 1 in this column in each of the examples, teacher 2 in each of the examples, and so on. And after that, we can rewrite this as a system of linear equations in this vector matrix notation. So this matrix X transpose multiplied by itself, multiplied by the unknown theta is equal to X transpose 1. And this is just a form of the, so if you think about it, this is the form of our linear system of equations. So where X transpose X is our matrix A, matrix of known coefficients, and B is X transpose 1. So just again, matrix and vector notation for this big system of linear equations, because we can have millions of features, and this still can be written in that form. So this is the matrix of known numbers, this is the vector of known numbers, this is the vector of unknown theta. That's the system of linear equations that we solve to get our coefficients, our parameters. And again, sometimes people, as you remember, write down the solution in this form. They write down the solution of the system of linear equations as A inverse multiplied by B. But we never really do the inversion in order to compute this. We use the algorithms such as Gaussian elimination to solve the system of linear equation. Even so, in many cases you will see that they write the solution for the linear regression in this form: X transpose X inverse multiplied by X transpose Y. Again, as a matter of convenience, even so, we never, as I said, really do the inversion. We solve the system of linear equations using algorithms such as Gaussian elimination. Yeah, it looks complex, but this is just a way to basically represent all this multi-dimensional data. Unfortunately, we have 2 dimensions. So we have examples and we have features. And examples and features. So that's why we have to work with matrices. So this matrix capital X is it's here for each of the features, x0, x1, x2 in every example. Features represent columns, examples represent rows. The same for the vector y. So each of those y's represent target variable in each of the examples from 1 to n. Okay. Looks complex, but there is nothing more than the fancy matrix representation of system of linear equations. which we solve for the unknown vector theta to compute the coefficients, unknown coefficients of our linear regression model. After we substitute those coefficients here, and then the new data comes in, the new features, we know the coefficients theta, we are able to compute our target variable y. That's all what is going on.
But in this last formula, so you take x, multiply on x, and multiply on tilde, and this is equal to x multiply on outcomes. So my question is, why we cannot multiply just x on tilde and it will be equal to outcome?
X multiplied by theta?
Yes. And it will be equal to outcome, to y.
So that's what we do here. So this is our linear equation, and we want to rewrite it in the vector and matrix form. So that's what we have here. X transpose multiplied by y. So this written in the matrix form. X transpose multiplied by y, and here it's x transpose multiplied by x. So this equation written in the matrix form. That's all. What we need.
This is minimization.
This is solution to the minimization problem.
Okay.
So because for this problem that we want to minimize, so this function, the cost function, is convex, quadratic, everywhere of course differentiable, continuous, and because we know this convex, we know that we already verified convexity. In order to find the point of minimum, we know that the first derivative should be equal to 0, the gradient should be equal to 0, we can solve this system of equations, and it happens to be, because our function is quadratic, the gradient of quadratic function is linear, this happens to be a system of linear equations, which we just written in the scalar form, and after we have rewritten it in the matrix and vector form. That's all. So this is just matrix and vector representation of this. But because it's really not convenient to write all the equations this way, we need to write down n equations in this form. So we basically introduce this notation for the matrix capital X, vector Y, and now this system of linear equation is written in a very concise matrix and vector form. That's all. It looks complex, but this is just system of linear equations. But because the number of features and the number of examples can be millions, of course, the only way to write it down concisely is introducing vectors and matrices. But nothing to be scared about. We know how to solve the system of linear equations. We know that those can be large. Of course, we're not going to do it by hand. We are going to do it in Python. So this is going to be solved by us. Just what we need to understand that, yes, for linear regression, there are two ways to solve it. Solve this system of linear equations called normal equations, or apply one of our favorite optimization algorithms. And because our gradient is linear, our equation is 0, so the Newton will converge in one iteration if we apply Newton to this, because it's going to be equivalent to this in any case. So Newton algorithm will just converge in one iteration because we get a system of linear equations instead of system of non-linear equations that we need to solve, just because our function is quadratic. If our function was non-linear, yeah, we had to iterate.
But here it is just an analytical solution, yeah? So no.
Yes, so this.
No iterative, but it's an analytical.
Exactly. So we are lucky because as a function we can have an analytical solution instead of doing the iteration. Even so, we can do the iterations. So, for instance, gradient descent algorithm. Many people solve linear regression with the gradient descent. In that case, you do iteration of gradient descent because it's not using quadratic information like Newton, so it will not converge in one iteration. You may do that instead of solving a system of linear equations. So one way or the other, really. Okay, questions? Before we go and see what can go wrong after this, or let's take a look at the Jupyter notebook for linear regression, so that we switch the gears, otherwise it's getting too heavy. So let's look, before we go anywhere further, let's look at the linear regression example. So, basically we have a very simple data set where the target variable are the sales of our product and the three features, additional sales. And the features are TV advertising budget, radio advertising budget, newspaper advertising budget. And we have a bunch of examples there. So very small data set that we can interpret. So we have 200 examples, and we have three features and one target variable. So 200 rows, four columns. We can plot, as always. Before we analyze anything, we plot. And because we have three features, we can plot separately each feature and the target variable. Sales versus TV advertising budget, sales versus radio advertising budget, and sales versus newspaper advertising budget. And we can immediately see that, yeah, here there is a potential linear trend for the TV advertising. Here maybe, but not necessarily. Here there is no linear trend at all for the newspaper advertising. We already get some ideas whether linear regression model may be appropriate or not. After that, yeah, let's start from simple linear regression with just one feature, the TV advertising. In this case, we can use a couple of Python package modules for solving linear regression, stats models, and scikit-learn. So we first do it with stat models, and after we do it with scikit-learn. Scikit-learn is pretty much standard Python package for machine learning. Stat models is more for statistics, but it also implements linear regression. So and after, so what we have the model which basically which says our target variable is sales, our feature, only one feature is TV advertising budget. We fit the model, which means solve this system of linear equations or to minimize the cost function, and after it brings the coefficients. Of course, we have two coefficients, we have intercept and we have slope. Yeah. So TV advertising is this and the intercept is that. So how do we interpret the model coefficients? So what it says is that a unit increase in the TV advertising spending is associated with additional 0.04 units increase in sales. Well, more convenient to multiply by $1,000. So in that case, additional $1,000 spent on the TV advertising is associated with increase in sales with 48 units of our product. That's how we interpret the results. So the intercept tell us basically how much we would sell without any additional advertisement on TV. That's how much we would say sell without any additional advertising. And now when we basically we fitted our model, we trained our model, we computed the unknown coefficients, beta or theta, whatever we call those, and after that, if we basically what we can verify, if we spend 50,000 on TV advertising, how many additional units of our product we would be able to sell, and basically we substitute this 50,000 budget instead of X. We already know the coefficients beta 0, beta 1. So we compute that, yeah, 9.4. What it means for, we would be able to sell additional 9,409 units of our product for 50,000 advertising budget on TV. So we can plot the regression line because we have only one feature, TV advertising budget. That's how the line that we figured looks like.
Why don't we have some kind of also confidence range?
We have. So we can basically look at the confidence intervals for the intercept, for the slope. And we can look at significance, so we can look at all the standard inputs, statistical inputs.
I mean already on predicted values. So because we state very specific number, yeah. If we let's say make this advertisement, then we will sell 9,000 widgets.
Yeah.
But should we take into account some error that we sell from this?
Yeah, and that's done with the help of this 95% confidence interval. So 95% confidence interval is this. So we would be, this 95% confidence, we will be able to sell this number of additional units in the range.
So that is for
between 42 units and 50 units.
Okay.
For each additional $1,000 spent on the advertising budget. Yeah, that's how we interpret it. So we can look at the linear regression as our hypothesis testing, can look at the p-values. So as you see in both cases, p-values are really small, close to zero. What it means? Because the p-values are smaller than 0.05. What it means? Those are significant. And all the significant coefficients, both the intercept and slope, are significant. And we also have seen it in other way. So when we look at the confidence interval will include zero, which means that those are significant. That's another way to look. So if zero is inside the confidence interval, it means those are not significant. Another way to interpret significance.
We reject null hypothesis that coefficient is zero.
Exactly. We reject null hypothesis that the slope of the TV advertising is zero, or beta 1 coefficient is zero. That's we rejected null hypothesis. So we have looked at the p-values. We can look at any other parameters. We can look at r squared, in this case 61%. We can look at f values and stuff like that, but here it doesn't really matter because we have only one regressor. After that, we can expand our regression to include all three features: TV advertising, radio advertising, newspaper advertising, and those are the coefficients that we would get from our linear regression model. So we have all these outputs. And in that case, yeah, the F statistic says that jointly these three coefficients are significant as well, very small number, and each of those are individual p-values are here. So p-values for intercept, TV, and radio are zero, but the p-value for the newspaper advertising is 0.86. What it means for the newspaper advertising? Yeah, it's not significant. So another way to look at it, here is the 95% confidence interval. You see zero is inside this 95% confidence, which means not significant. Another way to interpret it. You either look at p-values, or you look where zero is inside this 95% confidence interval. In this case, it's inside because the lower bound is negative, the upper bound is positive. So zero is inside.